consists of Jack Gibbons, Thomas Green, and Teresa Nozzle. We are working with Mott Corporation on determining sintering condition through non-microscopy-based techniques. Our faculty advisor is Dr. Zoe, and our industry advisors are Vincent Palumbo and James Steele. Our approaches investigated include scanning electron microscopy, which is the current technique used by Mott Corporation in determining sintering condition. This, however, is a qualitative approach that takes up to 60 minutes to complete. This team is investigating hardness testing and acoustic resonance testing as alternate methods. The goal is to create a pass-fail quantitative technique to determine sintering condition that takes a maximum of 5 minutes. Our samples are sintered 316L stainless steel discs. There are 2 control groups, F1 and F2. Samples A through D were sintered at a fixed time with a varied temperature in the oven. Samples E through H are at a fixed temperature with a varied time. There are 40 samples per variation.
Here's an SEM image of the control sample F2, and you can see the average outer diameter, which is the distance between the particles, is 24.25 microns, and the inner diameter of the pore is 6.875 microns on average. And the necking measurement, or the coalescence between the particles, averages in 18.67 microns in diameter. Compare that to an undersintered sample at 200 degrees below the control temperature. We had a similar average outer diameter, but the average inner diameter was 2 microns greater than the control, and the necking measurement was significantly less at 13.6 microns versus the 18.67 for the control. Then we have an over-sintered sample B, which was 100 degrees greater than the control temperature, and the inner diameter was 6.5 microns versus the 6.875 for the control, and the necking measurement was significantly greater at 31.15 microns versus the 18.67 microns for the control.
Acoustic resonance spectroscopy is a non-destructive technique that allows you to differentiate between good and bad parts. Each part has a unique fingerprint corresponding to its geometry, density, and material properties. If the part is defective or contains a crack, or in this case, under or over-sintered, the resonance spectra will shift. In the picture below, a part impacts a hammer, and the sound of this excitation is then recorded by a microphone. The microphone then records this unique signal, which an algorithm converts into a spectra that is unique to each part. The control samples in each variation were then tested in batches using our DIY fixture, and the results were used to investigate in what frequency the good parts corresponded to. This inspection occurred from around 0 to 94 kilohertz. Pictured to the right are just the results from just one sample, control sample F2. In the video below, you see one run. Through our testing, we found that its relationship between the resonance spectra of Mott's porous powder metal parts and the sintering condition. If a part was sintered for either too little time or too low of a temperature, the spectra shifted downward. The same trend is apparent in over-sintering, where the fingerprint shifted upward compared to the control samples. With this data, we are able to establish a criteria that the peaks must fall under so that it can be used to easily quantify if a part is good or bad. If it passes this criteria, it will then be able to tell in mere seconds if a part performs to spec.